Hello and welcome. So in this video we are going to implement the full adder circuit on the Fpga development board. The tool which I am using is Xilinx ISE 14.7. Now first of all we need to create the project. How? Go to File, New Project, Name Full Adder. You can type any name here, but as I mentioned earlier in my previous video that the best practice is to name the circuit which you are going to implement. So we are going to implement the full adder circuit. That's why I wrote here the full adder and circuit. Next, again family zinc board XC7010 board. Next, and finish. So now our project is created. Now we need to add three source files here. Number one is the .v file, which is basically the programming file or Verilog file, because we are programming in Verilog syntax. So that is why first source file which we need to add here is the .v file. Another file is basically the test bench file, Verilog test bench file. By the help of this test bench file, we can verify our logic or our program through the simulation. And the last file is basically the .ucf file, user constraint file, which basically is required to implement the program or implement our logic on the FPGA board. The UCF file is basically helps us to connect our input to the physical pins of the FPGA board. So first of all, in order to add the first source file .v file here, you will need to right click here, new source, Verilog module, full adder. Again you can type any name here, but best practice is to write the name of your project. Next, again as I told you earlier in my previous video that we have two ways to define our inputs and outputs. Either we can define our inputs and outputs here, or we can also type our inputs and output manually. So in this video I will add my input and outputs manually. So I'll just click here next and finish. So our .v file is created. Now because we have three inputs here, A, B and C in, so I need to define these inputs. Input A, input B, input C in, means carry in. And we have two outputs, sum and carry out. So output sum and output carry out. Alright, now so first of all we are going to implement the sum, which is basically A XOR B XOR C in. So assign sum is equals to A XOR B XOR C. Alright, C in, and similarly C out is equals to A and B. Assign C out means carry out is equals to A and B, which is going to add on C in into A XOR B. C in into A XOR B. Alright, so now our .v file is ready. Now we need to add another file, another constraint file, which is basically the test bench file, in order to verify this logic. So again right click here, new source, Verilog test fixture, and full adder underscore test bench. You can type any name here, but because we are going to implement the full adder test bench, so that's why I named it as full adder underscore tb means test bench. Next, and the unit under test is full header, or the file associate is full header. So now next, finish. Our test bench file created, and but we need to do some changes here in order to verify our logic. So we have 3 inputs, and here we have 3 inputs 0 0 0. This is the truth table of the full header. So I'm going to test the first 0 0 0 and then 0 0 1. I'm copying this and paste and paste and paste. 0 0 1 0 1 0 0 1 1, then 1 0 0, 1 0 1, 1 1 0, and then 1 1 1. It is not necessary to define each case, but for complete understanding I mentioned every case here. Alright, so now save this file, Ctrl S, and go to this simulation, click here, and first of all syntax check. There is no syntax error. Now simulate behavioral model. So here are the results of our full header circuit. I'm going to order this. I'm placing A here, B here, and C in here, and sum and out. Now when our all inputs are 0 0 0 0, our sum is 0 and our carry is also 0. When we have 0 0 1 input, 0 0 1, our sum is 1 and our carry out is 0. Now when we have 0 1 0, 0 1 0, our sum is again 1 and our carry out is 0. When we have two inputs 1, 0 1 1, B and C in are 1, so our sum is 0 and our carry is 1. As we can see on our truth table, when we have any two inputs 1, B and C in 1, sum is 0, carry in is 1. So here we can see that sum is 0 and carry out is 1. Now when we have 1 0 and 0, means for 1 0 0, again sum is 1 and carry is 0. Now 1 0 1, in 1 0 1 again we have two inputs are 1, A and C in, our sum is 0 and carry becomes high. And when we have 1 1 0, our sum is 0, our carry is 1. And when we have all our inputs 1, all our inputs are high, 1 1 1, our sum is 1 and our carry out is also 1. So our logic is verified, and now we are able to implement this logic to the hardware implementation board. So in order to implement it on the FPGA development board, we need to add another source file here, and that file, in order to add this file, we need to go to the implementation, click here, first of all click here, and then user constraint, click here, and post synthesis, click here. It will open some window for the in order to define some pins of the FPGA. It will open the window in order to connect the inputs to the physical pins of the FPGA. It will take some time. Click yes. Now So now close and click the schematic. This is the schematic diagram of our full adder circuit. Click here 5 IO ports. Here we have 3 inputs and 2 outputs. So now, as this is a FPGA board, these are our input switches and these are our output LEDs. So we need to define any 3 switches. So I'm going to define these 3 switches: G15, P15 and W13. So first input, which is A, I'm basically defining A, B and C. So our A is W13. A is W13. B is P15. P15, and the carry in is basically G15. G15. Alright, and we need to define 2 outputs, sum and carry out. So M15 is basically the sum LED. I'm going to define M15 and M14 the carry out LED. M14, yes, M14. And the standard voltage of these pins are LV-CMOS 33, means 3.3 volts. LV-CMOS 33. And Control S in order to save this design, and it will automatically add this design to the ISE projects. Here you can see full adder.ucf file automatically added by the this plan ahead 14.7 tool analyzer. So now we can see this file here. A is W13, B is associated with the physical pin of P15, carry in is G15, sum is M15 and carry out is M14, and all are the standard voltage of 3.3 volts. So now we are going to generate the bit file in order to implement or program the FPGA. So just double click here. It will take some time to generate the bit file. As you can see, bit file is created. Now in order to implement the bit file on the FPGA board, let's connect the development board to the PC. FPGA is connected to the PC. Now we need to go to configure target device and click OK. Impact window will open. We need to click here boundary scan, right click here initialize chain. FPGA board is selected, click yes and bypass and cancel. We need to click here and add. We need to select this full underscore adder bit file. Open the file, as you can see opened here. We need to click here and program the FPGA and select this FPGA device 7010. Click OK. The FPGA is successfully programmed. So this is our FPGA, and we can see it is successfully programmed because this green LED high, which indicates us the done bit, this done bit LED high when the FPGA is programmed, and this LED tells us that the FPGA is on, means powered on. Now here we have 4 input switches and 4 output LEDs. As we selected the input W13, P15 and G15, A, B and carry in, and we selected the output as M15 and M14, M15 as sum and M14 as carry. At this time all the inputs are 0, 0, 0, 0. At this time sum is also 0 and carry is also 0. When any one of the input becomes high, the sum LED, which is basically the M15 LED, becomes high. Now here I am turning on any LED. As we can see, sum LED becomes high. Now I am turning it again off, and when B is high, the sum LED also becomes high, and when A is high, sum LED also becomes high. Means in full adder, when any of the input is high, any one of the input is high, the sum LED is high, and when any two of the switches are high, the carry LED is high and sum LED becomes low. 1 and 2. When we have 0, 1, 1, at this stage of time 1 plus 1 is 2, and the binary of 2 is 1, 0. 0 is the sum and 1 is the carry. So here we can see the carry has one value, means high value, so the carry LED becomes high. Now when any of the two LED becomes high, carry input becomes high, carry output becomes high. Now when all of 3 inputs becomes high, our sum and our carry both becomes high. Why? Because 1 plus 1 plus 1 is equals to 3, and the binary of 3 is 1, 1. 1 as a sum and 1 as a carry. Now you will see all the 3 inputs are high, and our sum and carry both LEDs are on. So this is the implementation of the full adder circuit on Fpga ZYBO Z710 board, and this is for today's video. We'll see you on the next video. Take care.